Now we've got some of that maths out of the way, let's look at solving a differential equation for the motion of a mass acted on by some spring. It's going backwards and forwards in the x-coordinate. The force due to the spring is given by Hooke's law. F is equal to negative k times x, where k is the spring constant of this spring. Force is also equal to mass times acceleration, or mass x double dot. X double dot here is the second time derivative of x, which is the acceleration. Equating these two, we find that x double dot must be equal to negative k on m times x. So this is the differential equation that we wish to solve. We'll try a solution of the form e to the q times t. Q is some number, could be real or complex. And we'll substitute this into a differential equation and see what happens. So we need to know what the second derivative in time of this function is. Second derivative is q squared e to the q times t, because we get one factor of q for each derivative. And this is nothing more but than q squared times x. So x double dot is equal to q squared times x. Well, if q squared is equal to negative k on m, then we've solved our differential equation using this function. So that means q can be equal to plus or minus the square root of negative k on m. Taking out the negative sign into an I, we have plus minus I root k on m. If we call this root k on m omega, then we have plus minus I omega, which gives a solution x of t is c1 e to the plus I omega t plus c2 e to the negative I omega t. So this is our solution for x. It has two components, plus I omega and negative I omega, coming from the plus minus square root, and two constants, c1 and c2, that we can use to fit initial conditions, initial position and initial velocity. In general, we have one constant that we can fit for each derivative in our differential equation. So here we have a second derivative, so we need two constants to fit initial conditions. There are other ways of expressing this solution. We used an exponential function here to get the answer, but we could have instead used sinusoids like this. So if x is equal to b1 cos omega t plus b2 sine omega t, we can find values of b1 and b2 that would solve this equation with initial conditions. Or we could write it as a cos omega t plus phi, because remember, if you have two trig functions, the same frequency, you can condense it into a single trig function with some phase shift and some amplitude. Or this could be expressed as a, the amplitude, times the real part of e to the I omega t plus phi, because the real part of this is nothing more than the cos function. Now, these two solutions here, b1, b2 and a, are all real. Here c1 and c2 are complex, and so you might be worried that this whole function turns out to be a complex number, which is odd given that x should be real. Well, don't worry, because c1 and c2 are actually complex conjugates of one another, and that comes out naturally when you substitute in real initial conditions. When you solve for c1 and c2, they just come out to be the complex conjugate of each other. Let's now have a look at an example of using initial conditions to completely specify the solution to a differential equation. As an example, we'll have some spring constant or some mass, and time equal to 0, we have an initial position of 1 meter, initial velocity of 2 meters per second. So what's the equation of motion, and what is x as a function of time? Well, to find the equation of motion, all we need to know is the resonant frequency omega. The resonant frequency omega is root k on m, so that's root 200 on 2, which is 10 seconds to minus 1. So the equation of motion, x double dot is equal to negative omega squared times x, looks like this. X double dot is equal to negative omega squared, which is 100, times x. That's our equation of motion. What about finding x of t? Well, we'll assume a form x of t is equal to a e to the I omega t plus phi. What I mean here is actually the real part of this, but I'm not going to write it down because you'll find that physicists are often a bit lazy about specifying that they mean the real part. So when I write e to the I omega t like this, I mean the real part, but I'm not going to actually write it down until we need to at the end. So I use this form of x, and we have to fit a and phi to the initial conditions. How do we do that? Well, we know that x of t is a e to the I omega t plus phi. X dot of t, the velocity, we get a factor of I omega down, so I a omega e to the I omega t plus phi. And at time equal to 0, then we'll have two equations we can fit to these initial conditions. So at time equal to 0, the position is given by the real part of this, where the omega t has gone away because time is equal to 0. The real part of this is equal to a cos phi and that's equal to 1, which is the initial condition, time equal to 0. At time equal to 0, the velocity is given by the real part of all of this. Now, I times e to the I phi, the real part of that, well, the I here will multiply the I sine phi in e to the I phi, so we'll get a negative sine phi as the real part of this thing here. So substituting in the value for omega, we find the real part of this is negative 10a sine phi. That's the initial velocity, and that's equal to 2. So these two things here, they're simultaneous equations. We can solve for a and for phi. For phi first, we'll divide one equation by the other to get tan phi. Negative 10 tan phi is equal to 2. So tan phi is equal to negative 1 on 5. That's phi taken care of. To find a, we'll square these equations and add them together. So we get a cos squared plus sine squared we can take out, and that means that a is equal to root 26 on 5.